Hello students, myself Antara Bhusar, Assistant Professor of ECE Department of Guru Nanak Institute of Technology, and this is my lecture series on solid state device. And today we will discuss about a topic on Module 4, which is on field effect transistor. And today's topic is MOSFET, metal oxide semiconductor field effect transistor. And the subject is solid state devices, and the code is EC301. And the total lectures are 36 of this subject, and there are some course outcomes. Four course outcomes are there for this subject. First one is able to understand the energy band diagram, charge carrier transport phenomenon, and recombination generation process of different types of semiconductor materials. The second course outcome is able to understand the characteristics and current flow of semiconductor devices like BJT, JFET, MOSFET, and metal semiconductor junction and heterojunction devices. The third course outcome is able to analyze the design parameters of MOSFET, that is channel length and width, depletion width, surface field and potential, on resistance, transconductance, equivalent circuits, amplification factors, capacitances, noise margin, scaling and short channel effects of MOSFET. And the fourth course outcome is able to illustrate the rectifying properties of different types of junction diode, importance of reverse current in solar cell and light emitting diode, that is LED. Now, today we will discuss about metal oxide semiconductor field effect transistor. And today's course outcomes are second and third course outcome. In module 4, which is on field effect transistor, under this module there are different topics on junction field effect transistor and metal oxide field effect transistor, that is MOSFET. Already in previous lectures I have discussed about junction field effect transistor, what are the construction, field control action and characteristics of JFET, also pinch of voltage, about pinch of voltage, and some numerical problems. And in a previous lecture, I have discussed about some topics on MOSFET. That means under MOSFET there is MOS capacitor. In previous lecture, I have discussed about MOS structure under external bias, that is accumulation, depletion, and inversion phenomenon with energy band diagram. Also threshold voltage and plateau voltage. Today we will discuss about e-MOSFET and their characteristics. Now, what is MOSFET? That is metal oxide semiconductor field effect transistor. Now, this MOSFET, there is another name of this MOSFET, that is IGFET. That means insulated gate field effect transistor. Then the FET, which is operated in both depletion and enhancement of mode of operation. Now this figure shows how a practical MOSFET looks like. And here are the construction of a MOSFET. Now to to discuss about the construction of a MOSFET, we can see that the construction of a MOSFET is a bit similar to the FET, means field effect transistor. An oxide layer is deposited on the substrate to which the gate terminal is connected, and these oxide layers acts as an insulator like SiO2 that insulates from the substrate, and then the MOSFET has another name. You can say that as IG FET, that is insulated gate field effect transistor. In the construction of MOSFET, you can say a lightly doped substrate which is diffused with a heavily doped region, and depending upon the substrate which is used, they that they are called as p-type or n-type MOSFETs. Now this figure shows the construction of a MOSFET. There is a gate, drain and source, and the substrate is there, and that is the channel. Now the voltage at gate controls the operation of MOSFET. In this case, both positive and negative voltages can be applied on the gate as it is insulated from the channel. Now, with negative gate bias voltage, it acts as depletion MOSFET, while positive, if we apply a positive gate bias voltage, then it acts as an enhancement MOSFET. Now, there are some classifications of MOSFET. Depending upon the type of materials which is used in the construction of a MOSFET and the type of operation, the MOSFETs are classified as which is shown in this figure. That there are different two modes, that is enhancement mode and depletion mode. And in enhancement mode there is a p channel and n channel enhancement mode MOSFET, and also in depletion mode there is a p channel and n channel mode depletion mode MOSFET. And this PCH means p channel and NCH means n channel. Now let us go through the symbols of MOSFET. Now, the N-channel MOSFET are simply called as NMOS. This is enhancement mode, and that is depletion mode for N-channel MOSFET. And simply we can say N-channel MOSFET as NMOS, and also same for P-channel MOSFET. Same by simple version we can say that that is PMOS. Here are the symbols for enhancement mode and depletion mode p-channel MOSFET. Now let us go through the construction details of an N-channel MOSFET. Usually an N-channel MOSFET is considered for explanation as this one is mostly used. Okay, now this is the figure of a structure structure of an N-channel MOSFET. First, let us consider an N-channel MOSFET and a lightly in case of N-channel MOSFET, a lightly doped p-type substrate. A lightly doped p-type substrate which is taken into which two heavily doped n-type regions are diffused. That is, n plus means they are heavily doped, and these heavily doped n-type regions are diffused in the p-type substrate. And these two acts as source and drain. two parts, that is the source and that is the drain, and between these two N plus region there occurs a diffusion to form an N channel connecting drain to source. That part is diffused channel. Now a thin layer of silicon dioxide, that part, a thin layer of silicon dioxide is grown over the entire surface and holes are made. Here two holes are made to draw ohmic contacts for drain and source terminals. A conducting layer of aluminium, that is aluminum, that black portion. A conducting layer of aluminum is laid over the entire channel upon the silicon dioxide layer from source to drain, which makes the gate. And this SiO2 substrate is connected to the common or ground terminals. And the device can be operated in two modes, that in depletion mode or enhancement mode. Now we will discuss about the enhancement mode, but there may be a depletion mode. If the NMOS has to be worked in a depletion mode, then the gate terminal should be at negative potential when the drain is at positive potential. In that condition, the NMOS will be act as in depletion mode. But here we will discuss about the enhancement mode of MOSFET. Here, if we change the polarities of the depletion mode, for the depletion mode means if we change the polarities of the voltage, that is VGG. Here VGG is positive as shown in this figure. Now when no voltage is applied between the gate and source, if no voltage is applied between gate and source, some current flows due to the voltage between the drain and source. Now let some positive voltage is applied at VGG. Then the minority carriers, that is holes, get repelled and the majority carriers, that is electrons, gets attracted towards the SiO2 layer. This portion. With some amount of positive potential at VGG, a certain amount of drain current, that ID, flows through the source to drain. Source to drain. Now, when this positive potential is further increased, then the current ID also increases due to the flow of electrons from source, and these are pushed further due to the voltage applied at VGG. Now, the more positive the applied voltage VGG, the more the value of the drain current ID will be. Now, the current which flows gets enhanced due to the increase in electron flow, which is greater than the depletion mode, and this mode is termed as enhancement mode MOSFET. Now This is P-channel MOSFET. The construction and working of P-channel MOSFET means PMOS is same as NMOS, which I have discussed in previous slides. Now, a lightly doped N type of substrate is taken into which two heavily doped P plus regions are diffused, and these two P plus regions act as source and drain, and a thin layer of silicon dioxide is grown over the surface. Holes are cut through this layer to make the contacts with P plus region. And now the working of PMOS. When the gate terminal is given a negative potential, that is at VGG, then the drain source voltage, that is VDD, then due to the P plus region present, the whole current is increased through the diffused that P channel, and the PMOS works in enhancement mode. But if the gate terminal is given a positive potential at VGG, then the drain source voltage, that is VDD, due to the repulsion, the depletion occurs, due to which the flow of current reduces, and this then that PMOS works in depletion mode. Though the construction differs, the working is similar to both the type of MOSFETs, and also the change in the voltage polarity, both the types can be used in both the modes, means in enhancement mode or in depletion mode. This is the characteristics of MOSFET. Here first one is drain characteristics of MOSFET. Between the the characteristics are graph is shown in this figure. This is between the ID drain current, that is ID, and the drain source voltage, that is VDS. And this graph curve, characteristic curve, is for different values of inputs. Actually, when that VDS is increased, the drain current ID should increase. But due to the applied VGS, the drain current is controlled at certain level, and hence the gate current controls the output drain current. This is the drain current characteristics of MOSFET, and next is transfer characteristics, which defines the change in the value of VDS with the change in ID and VGS in both depletion and enhancement mode. And this curve is drawn for drain current versus gate to source voltage. That is transfer characteristics of MOSFET. Now next come to the drain current equation for linear and saturation region with the condition. Now if we consider an enhancement mode in channel MOSFET, then for a linear region, which is also known as ohmic mode, at that condition, when VGS greater than VTH, that is VGS get to source voltage and VTH is the threshold voltage, and when VDS, that is drain source voltage, less than VGS minus VTH, then the transistor is turned on, and a channel has been created which allows the current between the drain and the source. And the MOSFET operates like a resistor which is controlled by the gate voltage relative to both the source and drain voltage, and the current from drain to source is modeled as ID equal to mu n cox w by L within third bracket VGS minus VTH VDS minus VDS square by 2 into 1 plus lambda VDS. Here that mu n is the charge carrier effective mobility, and W is the gate width, and L is the gate length, and COX is the gate oxide capacitance per unit area. And the transition from the exponential subthreshold region to the region of linear to the linear region, that is not as sharp as the equation this equation shows. Okay, now there is another mode, that is saturation or active mode. At that mode the current equation will be this. That means when VGS greater than VTH and VTS greater than equal to VGS minus VTH, then the switch is turned on and a channel has been created which allows the current between the drain and source. Now, since the drain voltage is higher than the source voltage, the electrons spread out and conduction is not through a narrow channel but through a broader channel. And then the current equation will be this, that ID equal to mu n cox by 2 W by L into VGS minus VTH whole square to 1 plus lambda VGS minus VD set. That here additional factor is there, that lambda, here also lambda, that is that lambda is channel length modulation parameters, which models current dependence on drain voltage due to the channel length modulation. And all the other parameters is known, that is mu n is already I have said that mu n is the charge carrier effective mobility, and Cox it's the gate oxide capacitance per unit area, W is the gate width, and L is the gate length. Now, what is channel length modulation? Now, that condition that when if we consider the PMOS, that is P channel MOSFET, for PMOS, if the condition is VDS greater than VDS set, the channel charge which becomes pinch off, and any increase of that VDS which increases the drain current slightly. Now, the reason that the drain currents will increase for increasing drain to source voltage, which that is the cause of depletion layer width increases for increasing that drain to source voltage, and that effect is called as channel length modulation, and which is denoted by lambda, and the channel length modulation, that is the channel length modulation parameter. And this channel length modulation parameter ranges from approximately 0.1 for short channel devices and 0.01 for long channel devices. That's all for today. Again I am repeating that first was the MOSFET, that is metal oxide semiconductor field effect transistor, that is a real MOS capacitor MOSFET, which is shown in this figure. And then construction and classification of MOSFET depending on the operational mode, and also the type of materials which is used to construct a MOSFET. There are some classifications, and these are the symbols of MOSFET. N-channel MOSFET and P-channel MOSFET. N-channel MOSFET means NMOS and P-channel MOSFET is PMOS. And this is a symbol for enhancement mode and depletion mode in channel MOSFET, and these symbols are for PMOS in enhancement mode and in depletion mode. And next is construction of that in-channel MOSFET, and working principle of in-channel MOSFET in enhancement mode, and also the P-channel MOSFET I have discussed, and working principle is same as of P-channel in-channel MOSFET. And here are the characteristics of MOSFET, like drain characteristics and transfer characteristics of MOSFET. And this is the current equation for linear region, also which mode is known as ohmic mode, and that is the current equation for saturation or active mode. Here are different parameters, and the last is channel length modulation. That's all for today. In next class, we will discuss about more topics on MOSFET, and I am ending my today's lectures. Thank you.